Hello everyone, my name is Tyler Hill and I'm excited to share my final project with you. If you want, you can check out the code for that on my GitHub. I'll have a link to that available. But let's jump right in. So this is the main report for my analysis. I'm doing NVIDIA stock price time series forecasting analysis. This first code chunk sets everything up. So the overview is the project design. Like I said, I'm using daily NVIDIA open, high, low, close data, and I'm going to develop several different models for this: exponential smoothing, ARIMA, profit, KNN, as well as a long short-term memory recurrent neural network model, the last two of which are implemented in Python. So let's jump to the input data. I get my data for this project in Python actually, and I have a separate report that outlines how I do that. So let's jump over there really quick. So I'm developing an R-Shiny application to conduct stock price analysis to inform options trading strategies. And I decided to go with Python for gathering my data because it has this Y Finance library that does a really good job of grabbing data from the Yahoo Finance API. For my project, I'm using daily open, high, low, close data from NVIDIA, as I stated previously. With Y Finance, we can also grab a lot of other information. So like summary, their website, they even have like a logo, and all of this is useful information for building my R-Shiny application down the road. The other thing I do in this general function, get stunk, is to not only do I grab the daily history, I also calculate the exponential weighted moving average in a 12, 26, 50, and 200 day window. And then I guess before that, I also impute any missing values with this interpolate method in pandas. So that handles any missing data that may be present. And then so I'm just going to scroll down. This is all that useful information I might use in my application later. Here's my 12, 50, 26, 50, and 200 day moving averages. And then this is the open, high, low, close, as well as volume data for NVIDIA. You can see here just a plot of that data. So red is the closing data, and then blue is the 200 day weighted moving average. All right, so jumping back to the master main file where I do all my analysis, let's see, I use that reticulate R package to pull in that Python function here. That returned value needs to get processed pi to R here to be used in R. We can see that information is now in R here. I clean that up a little bit more, and then I wanted to visualize a candlestick plot with the exponential weighted moving averages on top. So I grabbed that data, I format it how I want, I get it into a time series object in R. I then plot it with high charts, which is a great way of charting things really quickly. You can see in just a few lines of code, I was able to make this interactive plot here, this interactive candlestick plot, showing the, if I zoom in even more, these are candlestick plots. If you're not familiar with those, there's links in the report, as well as the 12 and 26 day moving average, exponential weighted moving average is reported here, which is useful for performing stock analysis. All right, so moving on, I also decompose the closing price data because that's what I'm most interested in. So in a 365 or annual time frame, we get this decomposition. So this shows the observed values, the trend, and the seasonality, the annual seasonality, as well as the residuals or the randomness in the data. You can see that increases over time. I also compute the ACF and the PACF. You can learn more about there, but basically this is the autocorrelation function is useful for determining how you should transform your data to make it more stationary. And this is telling us that we should take a lag of 1, basically, in our differencing. But as far as like a transformation function, I explore which transformation function is best to use here in a custom function that does sort of a grid search on these 4, so the null, log, and square root and box transformations, as well as it looks at a lag of 1 or 2 for performing a rudimentary grid search on what the best transformation should be. It determines that a lag of 1 and a log transformation is best for this data. From the output, we can see a decomposition of that stationary series. It indeed looks way more stationary now. If we look at the PACF and ACF, we see that this is also showing us it's more stationary. And later actually look at the residuals too. And those are, you can kind of tell from here, those are more normally distributed around 0, 2, which is also good. I have a function here for splitting my data. I use a 70-20-10% split on training, validating, and testing for time series data. You don't randomly take different dates. You take them in chunks. So the first 70% is, so 1999 to 2014 is our train. Our validation set is 2015 to 2019. And then the test set, which I won't touch until the very end, is 2020 to 2022. So the first model I look at is exponential smoothing with the forecast package. ETS is a great function that sort of fits the hyperparameters for you really quickly. So calling ETS on the transformed training data, we get a model really quickly. Looking at the residuals of that, we can see that it's a good fit because our residuals are normally distributed, centered around 0. Also, our p-value for the long box text is good. When we make predictions using that fitted model, we see this, which we're getting our predictions in a transformed way, so we need to untransform those predictions. I made this custom function here to do that, and then I compile my predictions with that untransformed function as well as the original validation data and compare those directly in another high chart here. And we can see that just naively using the exponential smoothing, we don't get a very good forecast. But however, we do get a good forecast for the first little bit. It's just over time it diverges. Take the root mean squared error here. You can see it's that. I then compare that RMSE to a similar forecast, but using the untransformed, the original data. And we see that the RMSE is indeed worse. So then I talk about here about how I want to perform walk forward validation on a 5-day forecast because that's what I want to do with this information, right? With these models, I want to predict 5 days into the future to inform my options trading strategies. So I perform walk forward validation here, which takes a very long time to do because we're basically calling that ETS function a lot of times as we walk forward through our train and validate set making predictions. And we end up with this. This might look like, hey, we've perfectly forecasted the price, but on closer inspection, if we look and see what's actually going on here, so let's say, so here the closing stock price was 527 and our model predicted 544. So what was happening 5 days earlier with the closing price? The actual closing price was 543 and our prediction was 507. And so when we look 5 days into the future, it looks like our ETS function is just, all it's really doing is it's projecting its prediction is just what the price was 5 days ago. So this is kind of naive. It's not a really good strategy for trading. We would hopefully see even tighter correlations here. So that's not so great. I still take the RMSE of that. We can see that it's pretty low. I basically do the same thing for ARIMA. I'm going to speed through this for time's sake, but I look at whether I want to use the base auto ARIMA or a slower version of it. I opt for the slower version. I do the same thing where I just naively compute across the whole validation set on a single fit. I then redo that operation with walk forward validation. Again, this takes a very long time to run since it's recomputing it so many times. And I get, as you might expect, a similar result since ETS and ARIMA are kind of similar. And you can see it's just, let me zoom in again. It's just it's a similar story where it's really the predictions are just shifted in time. So here, 1, 2, 3, 4, 5 days later, that's the prediction that it was. The prediction is what it was 5 days prior. So not very good. I then explore Profit, which is a time series forecasting algorithm developed by Meta, aka Facebook. They have this available in Python as well. I do it here in R. And I just step through prepping the data specifically for what Profit expects to see. I then fit the Profit model. Profit comes with its own sort of decomposition. Profit's good because it's designed to handle seasonality well. And so we can see from Profit plot components that weekly seasonality and a yearly seasonality. So this might, help inform a trading strategy where we buy here and sell elsewhere, right? But anyway, I apply Profit in much the same manner as I did with the ETS and ARIMA. I make predictions, and this is a more familiar looking plot, right, that we saw earlier. So this is without the the validation, actual validation price data. These are profits predictions as well as a confidence interval. Over time it gets wider, obviously. But when we show the actual versus close, we can see that they're quite divergent. If we zoom in, yeah, we can see that they're quite divergent. So that's not good. I, again, calculate the RMSE on this sort of naive approach. It's similar to what we saw earlier, but a little bit worse. I then, again, do walk forward validation, blah, 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 skipping forward. We end up with this kind of crazy result. I think this is due to profit seasonality, and it cannot compute the exponential trend in the stock price very well. So what maybe I should have done, since this was done on the original data, since as per Profit's sort of documentation, it says it handles untransformed data, I just fed it that. So maybe I should redo this analysis with my with my transformed data. But this took a long time to do, and the results weren't very stellar. So I kind of suspect it would be the same as the ETS or ARIMA. So I'm going to keep moving along. I developed a KNN time series algorithm. This is a custom algorithm that I made in Python. I'm pretty proud of this because it actually works, and it was kind of fun to make. So KNN, if you want to learn more about that, I have a link to a really good KNN and time series, I should say. I have a link to a really good podcast that sort of motivated me to do this analysis, and you can follow along in the report here. But basically it takes Windows snapshots and compares it to the most recent Windows snapshot, and then kind of like it does the same thing that KNN that we explored in class does. It sorts those by some sort of distance, and then for the time series version of this, it sort of extrapolates into the future from those top Ks, and from that you can get predictions. Since I'm running pretty late on time, I won't go into the specifics here. I'll just scroll down to the end where we can see this is how it performed on the validation set, and we can see that it did pretty good. It's a little more nuanced, I guess, than the other approaches I've seen, and the mean squared error mean squared error isn't that bad. So let's jump back to here. I also, in Python, developed these long short-term memory recurrent neural network models. You can read more about that here and what those are. I'll just skip forward to the results again. So I messed around with a lot of hyperparameters to try to get the best fit. These are pretty finicky and take a long time to train. So I'm just going to keep skipping forward to the end where I built an ensemble that sort of takes two of the best performing models and takes an average from them. And you can see here the root mean squared error isn't that great, but I feel like this approach might be the best. This is also, I failed to mention, a multivariate approach. So it's not just looking at closing price data. This is actually looking at all of this data, and it takes all of this data and then computes what it thinks the 5 day in the future closing price might be. All right, try to wrap up quick here. So I then taking the exponential smoothing, the KNN, and the long short-term memory models make I make an ensemble, and I predict that on the test set. So this is the first time any of these models has seen the test set, and we can see here how the ensemble did on the test data, and it does pretty well. It's still not great for a live trading strategy, but I am pretty proud that I got at least this ensemble to work. We can see here that there's this really weird spike in the prediction, so it's kind of funny. Wonder what's happening there. I don't explicitly go into that here, but I do show the RMSE for all of the the average. So the mu would be the ensemble. So this is what the RMSE is for this, comparing the average with the actual, the ensemble predictions with the actual. And then there's the RMSE on the test set for the ETS, the KNN, and the LSTM. You can see that ETS did well, so that naive approach again, where we just sort of predict the same price 5 days later, is actually the best performing one out of all of these. So that again sort of validates how I don't think any of these models really do well for my intended business, quote unquote, use of informing options trading strategies. So this last set of code is just an ensemble function I built to predict into the future. So this is what on May 6th, and I'm recording this on May 3rd, This is what my ensemble prediction thinks it will be on May 6th. So my conclusion basically restates what I just said. I wouldn't use any of these models for a live trading strategy, but I learned a lot, and I want to keep exploring the LSTM RNN approach and integrate some other data into that as well. All right, thanks for hanging in there and for listening to my recording summarizing my final project.